Most BGP labs stop the moment the neighbors come up. You see established on 4 routers, you screenshot it, and you move on. This one keeps going. I built a 4-router eBGP ring in GNS3, automated the whole thing with Ansible, locked the polling channel down with SNMP v3, and pushed the neighbor state into a Grafana dashboard tied to BGP4 MIB. One repo, it rebuilds from scratch. Now let me walk you through it. This is the project. 4 routers, autonomous systems 65001 through 65004, paired as a ring. They are configured by Ansible and pulled over SNMP v3. They are rendered in a 6-panel Grafana dashboard pinned to BGP4 MIB. The numbers on the screen are the surface area. 4 routers, 8 neighbor relationships IV. You count them per router, which is how the dashboard counts them. 3 Ansible playbooks, 6 dashboard panels. Everything I'm about to show lives in one repo, and the link is on every slide. Before I get into automation or the dashboard, let me show you the topology, because one decision on this next slide drives everything else. We have 2 planes, and that is the whole point. The data plane is the BGP ring. R1 pairs with R2, R2 with R3, R3 with R4, and R4 back to R1. The transit links sit on /29s and the 10.0.0.1 through 10.0.0.4 range. Loopbacks are 1.1.1.1 through 4.4.4.4, that is 1 per router. This is a standard ring with nothing surprising going on here. The management plane is where the design choice lives. Everything monitoring related sits on a separate out-of-band segment located at 192.168.0.0/24. The GNS3 cloud node binds to a host tap interface, and the monitoring containers run on the same segment using network mode host. That means SNMP exporter, Prometheus, and Grafana are not writing the BGP ring to talk to the routers. They have their own path in. If you only take one thing from this slide, take this. If BGP breaks, your monitoring still works. You don't want to lose visibility the exact moment you need it. 3 things to call out here, and they're all decisions, not defaults. First, SNMP v3 at the auth priv level, with SHA for authentication and AES for encryption. Plus, there's an ACL restricting access to the management subnet. I went with v3 instead of v2c because v2c uses plain text community strings, and this repo is public. A community string in a config file in a public repo is a credential link. SNMP v3 with vaulted credentials is not. Second, ansible-vault at the per value level. The login password, the SNMP auth key, and the SNMP privacy key are all encrypted individually inside the host vars files. The structure of the YAML stays readable in diffs. Only the secrets are ciphertext. The vault password file is get-ignored and referenced from ansible.cfg, so nothing sensitive lands in a commit. Third, Grafana is provisioned, not clicked. The data source and BGP-health.json dashboard are mounted into the container. When the container starts, the dashboard is already there. There's a small JQ script that strips instance-specific metadata from the JSON before commit, so the dashboard is portable and does not drift between machines. The version numbers on the slide matter. Pinning the SNMP exporter, Prometheus, and Grafana versions means that this lab will rebuild the same way in a year as it does today. Three playbooks, and then Docker Compose up. That is the full deployment. The first playbook, deploy.yml, renders two Jinja 2 templates, one for interfaces, one for BGP. It pushes the rendered config through cisco.ios.ios_config. The snippet on screen is the BGP template. The router AS, router ID, and neighbor list all come from variables. You don't write per router configs by hand, you write one template and the 4 host vars files. The second playbook, verify.yml, is the safety net. It asserts that no BGP neighbor is in idle or active, and it pings loopbacks across the ring. If any neighbor is not established, the play fails, and you know before the dashboard does. The third playbook, configure-snmp.yml, pushes the SNMP v3 config and asserts that the monitoring group and the trap host both show up in the live SNMP output. Same pattern, configure, verify, and fail loudly if something is wrong. After this, Docker Compose brings up the 3 monitoring containers and the data starts flowing. You don't need to read the YAML and the Jinja side by side. Look at the structure. Variables on the right, template on the left. This is rendered config on the routers. That's the loop. We have 3 independent validation layers, and the word independent is doing real work here. At the router layer, Ansible asserts that no neighbor is idle or active, and it pings diagonally across the ring R1 to R3 and R2 to R4 to confirm end-to-end reachability. That's checking the routing protocol is functioning as we wish it to. At the SNMP layer, configure-snmp.yml asserts that the monitoring group and the configured trap host both appear and show SNMP output before the play exits. That's checking that the routers can actually be pulled. At the monitoring layer, Prometheus targets both the SNMP routers and SNMP BGP jobs as up across all 4 routers, and the dashboard reads 8 peerings, 8 established, and 0 not established on a healthy ring. That's checking that the polling pipeline made it all the way to the dashboard. If any one of these layers lies, the other 2 catch it. That is the point. You don't trust BGP alone, you don't trust SNMP alone, and you don't trust Grafana alone. This is a recap slide. I'm going to keep it short because the work is what speaks here. What this project exercises is BGP on cisco.ios across 4 autonomous systems with neighbor descriptions and advertised prefixes. Ansible with the inventory, group vars, host var split, Jinja 2 templating, vault and assert based validation. SNMP v3 at auth priv with views, groups, users, ACLs, and a trap host. The observability stack with SNMP exporter modules, Prometheus scrape jobs, PromQL using rate and changes, and alert rules with severity labels. Grafana provisioning and dashboard JSON management, and container orchestration with Docker Compose using network, mode, host, and pinned versions. That is 6 disciplines, none are theoretical, and all are wired into the same lab. Where it is now. This lab rebuilds end-to-end from the repo, 3 Ansible playbooks, SNMP v3 auth priv, 6-panel BGP for MIB dashboard with 3 alert rules. It's working, it is version penned, and it is documented. Next steps in roughly the order I take them. First, startup, config, persistence. Right now, if you reload the routers, the config drops. A simple write memory step in the playbook or a save.yml fixes that. Second, route the existing alert rules through Alert Manager to a Slack email or a webhook so the alerts actually go somewhere. Third, we're looking at a CI workflow that lints the Ansible, validates the snmp.yml, and runs the JQ strip on the dashboard. JSON before commit. Fourth, more topology depth. iBGP, route reflectors, route maps, so the BGP for MIB has a richer state to expose. Fifth, a second dashboard pulling from IOSv so you have link state alongside protocol state. Honest framing here. This project is not complete. It is a defensible checkpoint with a clear road map. In summary, we have one repo that rebuilds the whole lab. It's a 4-router eBGP ring in GNS3. It's configured by Ansible with vaulted secrets, pulled over SNMP v3, scraped by Prometheus, and it is rendered in a 6-panel Grafana dashboard tied to BGP for MIB with 3 alert rules. The GNS3 project file, the playbooks, the templates, the pre- and post-deployment configs, the monitoring configs, the dashboard JSON, the alert rules, and the cleanup script all live in the repo. The link is on the screen and it's in the description. So that's the build. Configuration is half the work. You are going to have to manually configure the routers in GNS3 to run Ansible. After that, this is more or less automated after you deploy everything. Okay, now we are going to cover the setup of GNS3. There is a separate README for this in the GNS3 folder. So I have loaded the GNS3 project file. I have started all 4 routers, and the cloud node is connected to the TAP0 interface. I am now going to go over into the terminal, into router 1, and go ahead and type enable and configure terminal. And per the directions in the GNS3 README, I am going to take the pre-deployment config and copy and paste that into the router. And now that we've done that, I am going to do the same thing for the other 3 routers. And it's important to note that the interfaces for the management plane will not be up by default. So we have to go into the interface and we have to no shut it. And after that, we can test ping. So ping 192.168.0.1. We have connectivity to R1. We have connectivity to R2. And we have connectivity to R3. And it's also important to note that the crypto keys will not automatically be generated. So we have to go in and generate them ourselves with the command crypto key generate RSA modulus 1024. Once we have done that, we can check the connectivity, the SSH connectivity, to each router. Now that we've done that, we can check SSH connectivity between each router. And SSH is good to R1. Now that we have established that SSH connectivity is good, it's time to deploy the Ansible playbooks. First, we're going to run Ansible playbook deploy.yml. And everything looks good there. Next, we are going to run Ansible playbook verify.yml. Everything looks good with Ansible playbook verify.yml, and for our last Ansible playbook, we are going to run ansible-playbook configure snmp.yml. Everything looks good there, and we are finally going to run docker compose up-d, and this is going to start SNMP exporter, Prometheus, and Grafana. So after we've done that, we are going to check to make sure Prometheus is up. We're going to go to HTTP 127.0.0.1 port 9090, and we are going to press the enter key. We're going to check alerts just to be thorough. Everything looks good there. And after that, we're going to go into Grafana. This is located at localhost port 3000. Okay, we have the Grafana login screen. Username is admin, password is admin. It's going to ask us to change the password. We are going to skip that. Now we're going to take a look at the dashboards, and there we have the default BGP health dashboard. And we're going to pull that up, and everything looks good there. If you note that the session uptime, the update rate, and the not established have a few quirks in there, and that is because GNS3 recently brought up the IOSv images. Okay, now we are going to check to see if Grafana is displaying to us a set of static values that do not change. And we are going to do this by first taking a look at the running configuration on router R1. And everything looks good there. So we're going to issue the router BGP 65001 command, and we are going to shut down both of these neighbor relationships. So we're going to issue the neighbor 10012 shutdown command and the neighbor 10044 shutdown command. So we're back in Grafana, and if you notice, the established number has changed to 4, and if we look at neighbor state, we have 1, 2, 3, 4 idle states, which is exactly the output that we would expect from issuing these two commands. And if we go back into the Prometheus alerts, under BGP peer not established, we have 1, 2, 3, 4 values of 1, which is idle, and here, which is again exactly what we would expect. And that's the lab of 4 routers, 8 eBGP sessions, Ansible building the configs, SNMP v3 polling them, Prometheus scraping, and Grafana showing you what is happening. Alerts fire when a session drop, and the whole thing rebuilds from the repo. The link is in the description, and thanks for watching.